All right, let's use this equation, the Henderson-Hasselbalch equation. Let's see how we can use it in the context of buffer solutions. So let's say I have a buffer solution that is 0.5 molar acetic acid and 0.5 molar acetate. The first question we want to answer is, what's the pH of this buffer as is? And so we'll see that the pH is equal to the pKa plus the log of A minus over HA. So in this case, instead of A minus, we have acetate, and HA, we have acetic acid. But we can figure this out. So the pKa of acetic acid is 4.74. We can get that from the table, or we can take the negative log of the Ka, whichever you have available. You can do that. So we have this. So the pH of this solution right now is 4.74 plus log of 0.500 divided by 0.500. Thankfully for us, log of 1 is 0, remember. The log of 1 is 0, that's defined, right? So that goes away. So the pH is simply 4.74. The pH is equal to our pKa here. Ta-da! We've done it. Problem 1 solved. But let's take a look at problem 2, because that's when the real fun begins. And I'm making this one a little easier. We can make it a little harder later. What's the pH if we add 0.1 molar of HCl? And again, we're going to assume no volume change. That's something we will have to worry about later. But let's not worry about that right now. Let's just assume that we're going to change our equilibrium a little bit. So adding 0.1 molar HCl is the same as adding 0.1 molar H+, right? That means that if we take a look at what our equilibria are, we're going to be essentially performing this reaction, right? We're going to be taking that H+ that's coming in, and we're going to convert it into acetic acid, sorry. So with this, we don't need to worry about doing any ice tables for this. This is generally because these are weak acids and weak bases. Putting a strong acid or strong base will fully react them. So we're not going to worry about having to do an ice table here, because we're throwing in so much H+, we're going to totally destroy the equilibrium, and we're going to completely drive all of that H+ away. All of that extra H+ is going to go away. So if we have 0.500 to begin with, and we want to get rid of this 0.100, we're going to subtract 0.100. I'm saying all the new acid that's being added, the 0.100 molar H+. That means we're going to be adding that amount to the acetic acid. I'm again not worrying about this H+, that's the added H+. So don't think of this as like, aha, now it's a neutral solution. It's not. But we're simplifying this just to see what happens. So by adding 0.1 mole of H+, 0.1 molar, sorry, we're going to consume 0.1 molar of our conjugate base, and we're going to make, therefore, 0.1 molar of our conjugate acid, our weak acid. And so now we can plug this in to our formula. pH is pKa plus log A minus over HA. And so the pH of this solution now will be our 4.74, that's our pKa, plus log of 0.4 over 0.6. So we have decreased the amount of conjugate base, we've increased the amount of weak acid, and so now we don't have something we can just cancel out, so time for your calculator. 4.74 plus log of 0.4 divided by 0.6. Make sure you've got your parentheses correct here. In doing so, 4.56 becomes our new pH, which is wonderful, right? It's not altogether that different from our original pH. And we've put in a crap ton of weak acid, or strong acid, right? We put in 0.1 molar HCl, 1/5 of the amount of that we had of our weak acid, right? But look, our pH has only changed just a little bit. Just a little bit. So overall, the point is that the buffers will resist major pH change. The pH of 0.1 molar HCl is 1, right? And we're adding that in, and we're not even decreasing this by even something very close to that. We're decreasing it by 0.2, 0.18 even, if I know how to do math properly. So we've decreased our pH just a little bit, even though we've added a lot of strong acid. And so that's how buffers work. So in either case, we're going to be adding or subtracting slight amounts off of our pH. In the next video, you should always be worried about this. Let's take a look at a more complicated one where we don't have assumed equal volume. Let's take a look at what that might